Okay, so we have our single particle theory. What we would like to do now is to formulate some questions that we can start answering with this theory. To do that, I'm going to need a tool, and that tool is called a spacetime diagram. Now, you may have seen spacetime diagrams before, but I would just like to review them so that we're for sure all on the same page. So what do you do when you draw a spacetime diagram? Well, you draw a diagram where the y-axis is time and the x-axis is space. And then you plot whatever it is, whatever object you're looking at on this diagram. So for example, let's plot the path that I'm following right now. Well, I'm sitting at my desk, I'm not moving anywhere. So let's say that my desk is at the position x is equal to 1. So we'll make this x is 1. And at time was minus 1, I was at x is 1. So I was sitting at this point. At time was 0, I was still at x is 1. At time is equal to plus 1, I am still at x is 1. And at time is equal to plus 2, I'm still at x is 1. So if we plot my trajectory through space-time, at all times, I'm just sitting at the same position at x is equal to 1. And there's some language that goes along with this. You would call this line that's showing you where I am in space-time, you would say, this is Robert's world line. Okay. Now, let's imagine that a ball is thrown, okay? And the ball is thrown from the origin. So from t is 0 and x is 0, that's where it starts. And it's thrown at a speed of 1 meter per second. So at 1 second, it's hit the 1 meter mark. At 2 seconds, it's hit the 2 meter mark. And this ball just keeps going with a constant velocity. Then this line over here would be the world line of the ball. So the idea of a space-time diagram is pretty simple. On the y-axis, we have time, t. On the x-axis, we have x. And then we plot the trajectory through space-time of some objects. Now, the fact that time is along the y-axis and position is along the x-axis can sometimes be a little confusing. So I want to just do a few more examples. Okay, so here is t, here is x, so x and t. And now let's imagine the following. We have an object moving through space-time. This is the space-time of object A. We have a second object moving through space-time. This is the world line of object B. So we've got the world line of object A and the world line of object B. And the question that I want to ask you is, who is moving faster, A or B? I don't want you to guess. I want you to think about it until you come to a definite answer, A or B. So pause the video now and only unpause when you have a definite answer. So pause. Okay, great. So now that you've got your definite answer, let's see who was moving faster, A or B. Actually, B. B moves faster. Let me see if I can convince you why I would say that. So they both start at the origin. At this time over here, okay, look how far A has moved. A has moved this distance. And look how far B has moved. Oh, I I should draw it over here. Look how far B has moved. B has moved this distance. So who moves the furthest distance? B. So who's moving faster? Well, that's B. And one of the things you see, and this is the thing that might be a little bit confusing to you, is the steeper the slope of the line, the slower the object is moving. In fact, look at the first diagram that we had. I was stationary. My line had an infinite gradient. The ball was moving. The green line, the world line of the ball, had a non-zero gradient. Here, A's gradient is steeper than B's gradient. A is moving more slowly than B. So if I put C over here, C is moving more slowly than A. A is moving more slowly than B, and B is moving more slowly than C. So the more, than D. So the more gentle your gradient, the faster you're going. D is going fastest. The steeper your gradient, the slower you're going. C has the steepest gradient, and it is moving most slowly. Now, what I want to do now is I want to ask, what is the world line of light? Okay, so there is T, here is X. I'm going to put a torch at the origin, and at T is equal to 0, I will send out a pulse of light. Okay, and then I want to draw the world line. So I need to know where the light is going to be at T is equal to 1, where it's going to be at T is equal to 2, where it's going to be at T is equal to 3. Now I have set C, the speed of light, to 1. Now remember that usually C is 3 times 10 to the 8 meters per second. So if I choose to measure T in seconds, it means that when I say X is 1 unit, or X is 2 units, or X is 3 units, each of these units is 3 times 10 to the 8 meters. So X is 1 actually corresponds to 3 times 10 to the 8 meters. X is 2 would correspond to 6 times 10 to the 8 meters, and so on. So when I've moved one distance of 1 in my new units, I've moved a distance of 3 times 10 to the 8 meters in my old units. And my world line, my pulse, starts at T is equal to 0 at the origin at X is equal to 0. And I would move through the point X is 1 at T is 1, because the speed of light is 1. I'd move to the point X is 2 when T is 2. And finally, I'd move through the point X is 3 at T is 3. So this is what the world line of light would look like, okay? The world line of light is a line of 45 degrees, or if you prefer radians, pi by 4 radians. That is the world line of light.